In this section, we're going to end the topic of determinants with an application to area and volume. We'll start with area, and I'll show you what I'm talking about. So for this, let A1 and A2 be vectors in R2. And throughout, whenever I write this, I'm talking about the matrix whose columns are those vectors. Let's draw a picture of the situation. So we may have something like this. There is vector A1. Perhaps that's vector A2. Between them, I have some sort of an angle. And while I'm at it, I'll be utilizing this angle as well. So I'll put an angle there. So I've got alpha and theta. Let me make my alpha a little more visible than what I have there. Alpha is this angle between the vectors, like that. Okay, first thing we can do is we can multiply A on the left by a rotation matrix. Let me call it R sub negative theta. And what R sub theta would look like, or R sub negative theta, would look like the following matrix. Cosine theta, sine theta, negative sine theta, and cosine theta. So in R2, when you multiply on the left by that matrix, the figure will move clock or counterclockwise theta. But if instead I make it negative theta, I should have just called that R of theta. If I wanted to go negative theta, like that's actually what I wanted to do, I'll put a little negative in there. Then we'll simply change the thetas to negative thetas inside the matrix. This way, when I multiply on the left by that matrix, it'll rotate theta clockwise. Now check this out. If I look at the determinant of R negative theta, that's the determinant, of course, of the matrix that I gave. When you take the determinant of that, I get cosine squared of negative theta plus sine squared of negative theta, which equals 1. So what does that mean? If I look at the determinant of R sub negative theta times A, I can break that up into the determinant of R sub negative theta times the determinant of A, and I have 1 times the determinant of A, which is the determinant of A. So applying this rotation matrix has done nothing to change the value of the determinant, but it has also achieved a second thing at the same time. After applying that matrix, this is what I now have. Oops. So now A1 is along the x-axis. And maybe I'll call it A1 prime because it's not the same A1 that it was before. I'll call this one A2 prime because they still have alpha between them. Now, when I'm talking about the area, let me come back to the original picture. I probably should have mentioned it, but I don't think I did. There is a parallelogram associated with these things. Do you remember the parallelogram rule for adding vectors? Well, we're not going to add vectors this time. I'm interested in the area of what I'm shading in here. That's what we're trying to find throughout all of this, is the area of that implied parallelogram. So now if you take a look at what we have now, let me go ahead and do this and reform my parallelogram if I can. Might be over here a little bit. That may or may not be a good representation of it. But by rotating the figure, I didn't change the area either. So neither the area nor the determinant has been changed yet. Let's locate a point up here. Let's call it XY. Now, and of course the x-axis is this way. On the x-axis, every point is of the form C times A1 prime, where C is a real number. This allows us to scooch to the left or to the right along the x-axis here by increasing or decreasing the size of this vector, and if C is negative, we can go in the opposite direction. But what you'll also remember here is up here, I have a line, let me call it L, and every single point on this line looks like the following. It looks like XY plus C times A1 prime. And now, we've talked about this before, so if you need to, you might want to look it up, but this creates a line that is parallel to A1 prime. So C is 0 at XY. When C is positive, we will move to the right. When C is negative, we will move to the left. Well, what we can do is take a look at this. If I allow the C to be some positive number, then I can move this until I get the following figure. I don't know what that is. Let's call it A2 double prime. These really don't matter at the end. And there's A1 prime. So now the area is more of a rectangle shape, like so. And we didn't change the determinant at all, because all we've really done here by taking XY plus CA1 is adding a multiple of one column to the other. In fact, we're adding a multiple of the first column to the second column. So you'll see something like this. Before this happened, we had A was equal to A1 prime, A2 prime, right? I don't know if I should call it maybe call it A prime as I move along, but the determinant is the same every single time. So we could call it A double prime if you want, but then we have something like this. That way you can see that it really is a column replacement. I should probably mention, you can do row replacements without changing the value of the determinant. You can also do column replacements because the determinant of the matrix is the same as the determinant of the transpose. So anything you can do the matrix, that is row operations, you can do also to the columns, because once you take the transpose, you can still operate on the rows, but you're really working on the columns of the original matrix. Anyways, this is what I have going so far. and the determinant is still the same. So the area, so the determinant is still the same. This still equals the determinant of A, and this is still equal to the original area. Why is it still the original area? Well, the rotation was no problem, but if you look at this parallelogram. Once I've pushed it over, I didn't change the height. So this thing still has the same height and the same base as before. So it has the same area as before. We can easily finish this off. By this time, I guess we could say A double prime is going to look something like this. Let's call it A11. I'm going to put a prime here, 0, and then 0, A2 double prime. Let me call it A22 so it's in the right spot. So now it's easy to see that the determinant is just going to be the product of the diagonal entries. And as I said, throughout we haven't changed the determinant, and here it matches the area of the figure, because we know that when I multiply these two entries, I'll get the base times the height. Let me write up a theorem. I'm not going to go through every single step of doing the theorem. It's kind of a pain, but you get the idea. Without changing the determinant, I'm able to compute the area with the determinant. So let's write this down. If A1 and A2 are vectors in R2, then they define a parallelogram so long as one is not a multiple of the other. I'll talk about that after this. Furthermore, if A is the matrix with those vectors as columns, then the determinant, well, I should actually, let me be careful here. The absolute value of the determinant of A equals the area of the parallelogram. And there's only a couple things I need to mention in the proof. I sort of did the whole proof already, but there's a couple of things. If A1 is a multiple of A2, then the determinant of A is equal to 0, because whenever the columns are linearly dependent, we get the determinant equal to 0. So the determinant's equal to 0, but look at the situation then. If we have one as a multiple of the other, then we have something like this. Like A1 would end there, but A2 would end there. If one is simply a multiple of the other, well, then they contain no area, and so the determinant being 0 does equal the area in that case. Secondly, we need absolute value because if you swap columns, you get the negative of the determinant. Well, no matter what, the determinant can be positive or negative, but the area is never negative. So we need absolute values, because what you call A1 and A2, I may somehow call A2 and A1. I'll flip the columns inadvertently, and I'll get a negative of your answer, but once we throw the absolute values around everything, it takes care of that. as an example, find the area of the parallelogram with vertices 0, 0, negative 2, 4, 4, negative 5, 2, negative 1. Let's draw a picture here just to get an idea of what we're dealing with. 0, 0, of course, is pretty easy. That's right there in the center. Negative 2, 4. Let me see. Negative 2, 4. If I go to the left, negative 2, and then up 4. Let's put that there. Let's call that negative 2, 4. If I have to, I'll graph it on a graph paper if I really need some more accuracy than this. But I may or may not. Then I have 4, negative 5. So I'll go out to, I think, what's 4, and then go to negative 5. We'll see if about there. Oh, I had it where I wanted it. 4, negative 5. And then we had one more, 2, negative 1. Where's 2, negative 1? 2. Let's put it about there, negative 1. Now let's take a look and see what we have. I'm going to connect these like so. So it looks to me like here's a corner, here's a corner, here's a corner, and here's a corner. So, and it looks like then that this vector is one that I want right here. You darken it in. And this vector here is one that I want. So when we set up our matrix, I want the determinant of, so this matrix, this vector here is negative 2, 4, so negative 2, 4. And down here we have 4, negative 5. And that equals 10 minus 16, which is negative 6. We need to take the absolute value of it to get the area. Next, these determinants actually also do volume. This time you can use 3 vectors to determine what you want. All right, we'll say that's vector A3. Make this easy on myself. A2. A1. All right, let's see what we have then here. Got that guy right there. All right, now let me do A1 and A2. All right, I got that guy there, and then A3 and A1. Try to go for as long as A1 is there, and then here, like so. Looks like I got what I want. And then now let me go ahead and finish this box off. There, I think I got my nice three-dimensional figure there. Okay, so we start with this. This is the thing that I'm going to try to find the volume with. My columns for my matrix will consist of these 3 vectors. Right, now I have to show how I can start with just a general volume and get it back to where I want. Now I can't go into as much detail because it will become so painful as I did on the last one, but I can explain what everything's doing. By rotating in each plane, we can get the parallel piped to be flat. So what's flatness going to look like? Something like this. Okay, so I think I've got it. Now, the way it's going to look on the XY axis will be something like this. I'll get it to where, let me see if I can get this to be straight up and down. All right, the only thing that's missing here right now is the fact that it's not, and it might jut back that way a little bit behind the y-axis. Well, what I can do to make it cube shape is the first thing I can do is shore up whatever's back here. If the shape is actually farther out, like that, say, then what I can do is apply the thing that I had before. This would be in the R2 direction, so I could take, and since I want to go horizontal, or want to go parallel to the x-axis with this and bring this in until it meets up with the y-axis, what we'll need to do is you'll have something of this form, A prime, who knows what it is by now, but maybe we've gotten to this point so far. And then all I have to do is add a multiple of the first column to the second column. So like CA1 prime plus A2 prime, and then leave the A3 prime alone. And let's go back to what we had. We did rotational matrices in order to get this thing flat. Okay, none of those changed the determinant. In fact, when I want to do a rotation about a given plane, check this out. This matrix will rotate about in the XY plane. It will rotate the figure an angle theta. So now all I have to do, if I want to rotate in the other planes, if I want to rotate, say, where the y axis is the thing we rotate about, but we rotate within the XZ plane, then if I was rotating in the XZ plane, I would leave this column alone. This column would go to the third column, and in the middle I would have 0, 1, 0. Similarly, if I wanted to rotate, say, where I am going about the x-axis, but y and z, I'm rotating in that plane, then I will have, for the y, I'll have this first column will go to the second, the second column will go to the third, and the 0, 0, 1 will come to the first column, but it will be 1, 0, 0. So that's how you do rotational matrices. All of these have determinant 1, so they change nothing. Then when we do this, we know that a column replacement doesn't change anything either. Then to try to get this so that will take care of this extra stuff when I can now erase that stuff out of here. It's no longer necessary. See what I can take out of there. So now it's up against the y-axis. The only problem now is I need to move it in this direction a little bit so that it snugs up against the xz plane. How do you get it to do that way? Well, you can see that that vector is parallel to whatever this A2 vector, whatever version of A2 this is, and maybe this is, I don't know, A2 double prime. So up here then, what we'll do is we will add a multiple of A2 double prime to the third column, to the z column, so that this moves over until it gets up to the xz plane. So to move that over, you're going to have to get a new matrix from the old one. Here we'll still have our A1 prime. We had an A2. This stuff here was A2 double prime. So the third column then would be A3 prime plus some multiple of A2 double prime. And that will finally snug it up against the xz plane, and you'll be left with a nice rectangular figure that looks something like the following. And by the time you get here, maybe this is A1, what are we doing? A1 prime. A1 was not affected by that last thing. Then we had an A2 double prime. And then let's call this A3 double prime. But what's going to happen here at the end is your matrix, these vectors that we have here have only one component. This has only an x component, this has only a y component, and this has only a z component. So you're going to be left with something along these lines. I'm just going to let these be numbers. And now it's easy to see that the volume will be given by that determinant. So throughout this, the volume hasn't been unchanged. Let me come back to this. When I took this and smushed it against the xz plane, I didn't change the height of the figure. So the base was the same and the height is not changed, which means that the volume is the same through that process. So nowhere has the volume been changed or the determinant. Here's a theorem. If the vectors A1, A2, and A3 are all in R3, let's say they define a parallel pipette. Then the absolute value of the determinant of A1, A2, A3, I don't know why I put commas between them. We don't usually put them between there when there's a matrix. So, and once again, I'm not bothering with the cases where you might have two of the vectors being multiple, one being a multiple of the other, or one being a linear combination of the other vectors, because in all of those cases, you'll get a figure whose volume is 0, and that will match the volume of the determinant. I'm simply worried about the situation. I'm only caring about the situation where we have the three of these things actually defining a real honest parallel pipette that will have volume bigger than 0. So the absolute value is there to handle column swaps. As an example, find the volume of the parallel pipette with one vertex at 0, 0, 0 and the other vertices at 1, 3, 0. negative 2, 0, 2, negative 1, 3, negative 1. And there's really not a whole lot to be doing here. Let's find the determinant of the following matrix. Just write these down in vertical fashion. And then when I expand this, I think I'm going to go down along the first column because there is a 0 there. So let's go ahead and do that. 1 times, so let me go ahead and cross out the row and the column, and we have 0, 3, 2, negative 1. And then we have minus, the next entry was a 3. And let's go ahead and pull that row and that column, and we have negative 2, negative 1, 2, negative 1. And of course the 0 doesn't do anything, so I'm not going to bother with it. Let's see what we get. I get negative 6 for the first piece, and for the other piece it looks like I'll have 2 plus 2 will be 4. That's negative 18, and to get our volume then, we take the absolute value of that. Next, let me show you how linear transformations affect area and volume as well. So we'll start with a theorem. Let t from r squared into r squared be a linear transformation. Let A be the standard matrix for T. And to remind you what that means T of a vector equals A times that vector. If S is a parallelogram, in R2, then the area of the image of that figure equals the absolute value of the determinant of A times the area of S. The proof: let B1, B2 be vectors in R2. The parallelogram determined by B1 and B2 is, so this is the actual mathematical definition of the parallelogram. So let's call it S1 B1 plus S2 B2 such that S1 and S2 are in 0, 1. All that is telling us that we're gathering every point along B1 until we get all the way to B1, and then every point along B2 until we get to the end of B2. So 0 starts at the origin. By the time it gets to 1, we have filled out B1 and we filled out B2. This is nothing more than a linear combination of those two vectors. So as S1 and S2 go from 0 to 1, we trace out a figure. Who knows what it may be like, but this may be B1. This may be B2. And then as you allow S1 and S2 to go to 0, 1, you'll be going up along here and up along here. And then when you add them, you'll be taking care of all of those points that are the sum of the two semi-vectors as you're tracing them out. So you'll get the whole figure, is all I'm saying. Now, you don't get the interior of it. You just get, I probably shouldn't have put the interior in there. You only get the outer portion, but we do want the area inside of there. So anyways, this is what S looks like. So the area of S is the determinant of B1, B2. Then let's take a look and see what T of S is. So it's got the same general outline to it. In fact, we're going to get a parallelogram in R2, but this time, who knows what that thing did to it. Maybe one of them is like down here. Perhaps that's T of B1. Who knows where the other one went? Maybe this is T of B2. But as the S's go between 0 and 1, you're surely going to trace out a parallelogram, and that's the area that we're trying to figure out. Or in any case, T of S, another way we can write it is S1. Instead of T of B1, I can call it AB1. Remember, matrix A was the standard matrix for this linear transformation. All right, so there's T of S. Its area. So once again, we can put a vector, well, the area, let's do it this way, of T of S then is equal to the determinant of the matrix with columns A, B1, A, B2. And I need absolute values around that thing. That's the absolute value of the determinant of, let's do this, A, B1, B2. And that's the determinant of A, and that's, we'll call that B. Did I call that B yet? Let me see if I did that anywhere. No, but that's what I'm referring to. B then just because I can't remember if I used that before. Well, we can break these up. Absolute value, you certainly are allowed to break those up too. And so there's the determinant of A. The determinant of B, well, the original matrix was B actually. So this equals the determinant of A times the area of S. As an example, let the parallelogram S be determined by the vectors B1 equals 4, -7, B2 equals 0, 1. Let t from R2 to R2 be a linear transformation with standard matrix A equals 5, 1, 2, 1. Compute the area of the image of S under T. So for my solution, T of S, well, the area of T of S, I should actually say that area of, that's the thing they're looking for. That is the determinant of A times the area of S. And well, let's throw these things in here. Let's go ahead and put it in. That's 5, 1, 2, 1. I'm using DET throughout this lecture so that you don't confuse the determinant with the absolute values in this thing. And the area of S, what were those B's again? They were 4, negative 7, 0, 1. All right, let's see what I have here. 5 minus 2 is 3. That doesn't change anything. How about the other one? Just 4? I didn't need the absolute values at all in this case. Another theorem. Let T from R3 into R3 be a linear transformation with standard matrix A. If S is a parallel pipette, in R3, then the volume of T of S equals the absolute value of the determinant of A times the volume of S. So the proof I'm going to do not exactly completely 100% in detail, just because it follows so closely to the other proof. We can define the parallel pipette in a fashion that is completely analogous to a parallelogram. And then once I say that S1, S2, and S3 are in 0, 1, then you are physically creating a parallel pipette. Parallel pipette has parallel sides and things of that nature, but every single face of a parallel pipette is a parallelogram. And as before, T of S is going to be the same thing. Because T is a linear combination, I can slide all the constants or all the scalars out front like so. And of course then the volume of T of S is going to be the absolute value of the determinant of let me see how I want to write it. AB1, AB2, AB3. Remember, this TB1 is AB1, TB2 is AB2. Well, you get the idea. And I can play the same game as I did before. This is the determinant of the matrix A times B1, B2, B3. And that, of course, will be the determinant of AB, which I can break up. There is one last application here that I think I would like you to see. Oh, before I do go there, let me come back for a second here. There's something very important that I want to mention. Right here, the volume of S is very much involved in the volume of T of S. We could think of S almost like being a little coordinate system all of its own, almost as if like a closed interval, if you will, but in 3 dimensions. What I'm saying is this. The x or the vectors are coming from inside of this parallel pipette. Now, as the vectors become arbitrarily small, this volume will become arbitrarily small. That means the volume of the image will become arbitrarily small. The same thing happens with area. As the area of S becomes small, the area of the image becomes small. That means that these linear transformations are continuous functions. Since they're continuous, there's a lot of things they can do. So, let's suppose, so far I've been able to do areas and volumes of parallel pipettes and things like that. But what about an area, what about something stranger like this? Well, what you can do with these things is you can create a mesh inside of them, like so. And all of these things I'm capable of finding with determinants. However, I can keep making smaller and smaller rectangles inside of here. You probably saw this when you were doing integrals and Riemann sums. This is similar to that nature. As I'm getting closer to these edges, let's blow this piece up. And I have blocks that are going something like this maybe. All those being done, I can do tiny little blocks in here. And because of continuity, I can make them as small as I want. As you might expect, then I can use some sort of a limiting process to be able to get areas that are not exactly square or rectangular in shape, but they can be circular in shape as well. And the same kind of a formula holds. It goes something like this. If S is a region of finite area / volume, then the area or volume of T of S will still equal the absolute value of the determinant of A times the area / volume of S. The proof of this stuff is a little beyond, it's not really beyond, I mean everything that we do to prove it is something you should be able to understand. but it is outside of the scope of this course. So we're not going to take a limit and actually come up with what this is, the exact details and everything like that. So I will just go ahead and end this lecture there.